Welcome back, everyone. Thank you for being here. Welcome to another coffee shop, Astrophysics. So, if you don't know who we are a group of graduate students and postdocs from UWM, and we all work at the Center for Gravitation, Cosmology, and Astrophysics. And Anodyne is kind enough to let us give a talk here once a month during the semester. So, this is all of us. And if you have any ideas or topics you'd be interested in seeing us kind of talk about here, please let us know at this email right here. So for those of you that will be in Madison and missed our talk on aliens last semester, we will be giving that talk again in conjunction with Astronomy on Tap from UW-Madison, our sister organization. So if you're in town, feel free to check it out. For today, your speakers are myself, Shashwat, Kumar, and Sarah, and we will be talking about the auroras. So we hope you enjoy, and I'll hand it over to Kumar.
All right, good afternoon, everyone. Thanks for coming. What a turnout. Uh, can you guys hear me okay? Right, that's better. All right, so we're talking about auroras today. And, well, the first question is, what are auroras? So auroras are basically a light show basically formed when charged particles from the sun interacts with Earth's atmosphere. And these interactions create these glowing rivers of light that you can see, especially near the poles. And the colors that you see, I mean, it's very vibrant, but the colors, specific colors depend on the type of gas that these particles interact with and also the altitude of interaction. Sometimes the sun goes through the phase where it releases a lot of charged particles, and we call this the high solar activity phase. And during this time, auroras are stronger and happens more frequently. In a nutshell, this is how it forms. So there is charged particles coming from the sun, what we call a solar wind, and it interacts with Earth's own magnetic field. So today's talk, we're going to split into three. I'll talk about how these charged particles come from the sun and sun in general. And Josh will talk about Earth and how these charged particles interact with the magnetic field of Earth. And Sarah will talk about auroras on planets other than Earth, so other planets in the solar system and beyond. So, the sun. Well, the sun is weird. It has a lot of charged particles. It's a hot ball of plasma, and it gives us light, it gives us heat, but it also releases a ton of charged particles into space all the time. So the sun's outer layers are constantly moving, and that fuels its activity. The layer of sun that you see when you look at it, do not look at the sun directly. If you look at it through like a filter or something, then that layer of the sun that you see, the layer where the light comes from, is called the photosphere. And you also see these dark blobs on the photosphere. These blobs are called sunspots, and they are these little dark regions that you can see on the photosphere, and they're dark because they're a little bit cooler than the surrounding photosphere. So photosphere in general has a higher temperature, but this one has a slightly lower temperature, so it looks a little bit darker than the rest. And the number of sunspots that you see on the photosphere is directly correlated to how active the sun is. So if you see a lot more sunspots, that means the sun is a lot more active. And by a lot more active, I mean there is a lot more charged particles coming out of the sun during that time. And we'll see why in a second. But to understand why charged particles get released in the first place, it's important to know what a magnetic field is. So magnetic field is a region around a magnetic object or moving charge where you can feel the magnetic forces. So for a bar magnet, you can kind of visualize the magnetic field around it by dropping a bunch of iron filings on it. And it'll orient looking something like that. Same thing happens if there is a wire carrying a charge or carrying a current. There will be a magnetic field around that current carrying wire. And the sun is nothing but a bunch of moving charges, right? Like there's a lot of ions just constantly in motion. So there is a magnetic field associated with the motion of the ions on the sun. And sun's magnetic field looks something like that. It's a lot more complicated than just a bar magnet or a current carrying wire. And it is because of a bunch of reasons. So if the sun were like Earth, like let's say it was a rock just rotating, then the magnetic fields would look a little bit simpler in that it goes from the south to north inside the sphere and then loops back around outside. But the sun is just like I said, plasma, it's all goo. So it does not rotate like Earth does. Different layers of different parts of the sun rotates at different speeds. And this is called differential rotation, just means different layers of the sun rotates at different speeds. So the equator of the sun moves a lot faster than the poles or anywhere near the poles. So the magnetic fields are affected by this rotation. So as time goes on, the magnetic field gets dragged with the rotation. So the center part drags this a lot faster than the poles do. And over time, the magnetic field just spirals and loops around and then creates a whole bunch of things. And I'll show how that kind of looks. So it, in addition to it winding, it also can twist and snap. And in a sense, it looks like this. So here you can see the magnetic field lines on the photosphere and also how it goes outside the photosphere. Also notice that when there are sunspots, you'll see a lot more magnetic field loops and stuff. Here's a close-up of it, so you can see how many more field lines there are on the sun when there is a lot more sunspots. So the magnetic field of the sun is the reason why charged particles get ejected out, and we'll see why by looking at what solar flares are. So in the first image, you can see, if you pay attention to the white lines, you can kind of see how it snaps and ejects a bunch of stuff into space. And that's exactly what causes a solar flare. So charged particles will travel along this loop, and then when the loop realigns, it just gets ejected into space. And this release of charged particles creates a strong electromagnetic radiation that propels outwards and goes into space. And if we get hit by it, then it can disrupt radio communications and satellites. And like we said before, if there are a lot more sunspots, a lot more of these can happen. And once they get to Earth, we get to see a lot more auroras. And here's a video of how that kind of looks like. So you can see a bunch of charged particles moving along the magnetic field line on the photosphere, and then it just gets ejected once the magnetic field realigns. I'll let it play one more time. All right. So that's the photosphere. So that's the layer of the sun the layer of the sun the light comes out of. But sun also has this outer atmosphere, which is something we cannot see even if you look at it through a filter, but you can see it if you block the region of the photosphere. And you can do it in two ways. You can either literally tape a piece of paper on the telescope where the sun is, or you can wait for a solar eclipse. And this image here shows what the sun looks like during a total solar eclipse. So when the photosphere is blocked by the moon, you can see the stuff around it. And this is the sun's corona. It's the sun's outer atmosphere. And this extends millions of kilometers beyond the photosphere. So it's a big region. And it's very hot. Its temperature reaches over 1,000,000 degrees. And this region constantly expands outward, kind of like a giant fan in space constantly pushing stuff out of it. And the wind produced by the sun is called a solar wind, and it just carries away a bunch of these charged particles away from the sun. So solar wind, again, continuous stream of particles that move from the sun's corona outwards into space. And the particles within the solar wind, its speed ranges from about 300 to 800 kilometers per second, meaning that it can cross the entire width of the US in a matter of few seconds. The particles within the solar wind are mostly electrons, protons, and helium, helium nuclei, and a little bit of traces of other ions. So this solar wind, it moves out into space. Part of it moves towards Earth, and when it interacts with Earth's magnetic field, that's when you get auroras. So another thing sun does is coronal mass ejection. It's same as a bunch of solar flares happening in quick succession. So during periods of high solar activity, meaning if you look at the sun, there's a bunch of sunspots, it just means that there's a lot more charged particles being released in quick succession. So here you can see the photosphere is blocked, and then the surrounding area, the corona of the sun, you can see how these particles get ejected out into space. And we're talking a bunch of particles. So these are, the coronal mass ejection is just a massive eruption of plasma from the sun, and they travel along the solar wind carries it from the sun out into space, and it can reach Earth just in a matter of few days. A direct hit from one of these things can cause a giant geomagnetic storm, and we'll look at the impact of coronal mass ejections and how it can affect auroras now. So here's a video of how these coronal mass ejections happen in a span of 3 days. So you can, if you keep looking, you can see how these giant eruptions take place once in a while, and like it gets carried away from the sun by solar wind. So during a coronal mass ejection, auroras, like you probably guessed, are much stronger. You can not just brighter, it just you can see them further south. So usually you can only see it near the poles, but during a coronal mass ejection, you can see it further, well, south or further north, from depending on which pole you're looking at. Since they are charged particles, it can disrupt power grids and damage satellites. Basically, electrical infrastructure will be under threat. And similarly, with satellites gone means it'll affect the GPS or navigation or communication and so on. So understanding coronal mass ejections helps us prepare for solar storm impacts in the future. The sun also goes through a period of high solar activity and low solar activity, and this cycle happens every 11 years. High solar activity means more sunspots, more solar flares, more chances of auroras and coronal mass ejections, and a solar minimum is the opposite, so fewer sunspots, fewer solar flares, and weaker solar storms. So tracking this solar cycle can help us predict space weather events. This year in particular is special because we are at a solar maximum. So during our current solar cycle, we're at the peak of that solar cycle, meaning this year we have a lot more sunspots, a lot more solar flares, and a higher probability of coronal mass ejections, and higher possibility of being in a geomagnetic storm. So should we be worried about this? Well, in 1859, there was a massive geomagnetic storm that was recorded called the Carrington event, and it caused auroras to be visible near the equator. I mean, it was so many particles, and we could see it. It even caused the telegraph systems to fail worldwide. The illustration here is a sketch by Richard Carrington, who was an astronomer who observed the sun during this Carrington event, and it's named after him. And he sketched the sunspots on the sun. And if you look carefully, you see the labels A, B, C, and D. It just shows where the solar flares are coming from. So, should we be worried? Well, it really depends on how much we know, right? So for most solar events, solar storms, it has minimal effect on our modern day technology. We know this is going to happen, so we shield it in preparation for um, a potential solar storm. But severe storms like the Carrington event could disrupt GPS and communication and satellites and basically every electrical infrastructure. So it's important to monitor the sun's activity almost daily so that we can better prepare for an event like this. And scientists do this essentially on a daily basis. They monitor the sun, they look at how many sunspots there are, and predict where that peak and how much we should be worried about. So with improved forecasting and prediction, the risks to daily life still remains low. Right, so that's the sun. Hopefully it's clear how particles get ejected from the sun and travel towards Earth. And now I'll hand it over to Shash to talk about how these particles interact with Earth's magnetic field and cause auroras. Thank you.
Yeah, thank you, Kumar. So now you've heard about what happens at the sun and how it ejects all these particles. That ends up being the solar wind. And so I'll talk about how that interacts with the Earth's own magnetic field and how we get to auroras, basically. So to start off with, the Earth has a magnetic field. If you were at our last talk, this was briefly touched upon. But basically, in the interior of the Earth, we have this region called the outer core, which is made of molten metals, a lot of which are magnetic in nature. So when you have hot liquid metals moving around and sloshing inside the Earth, you basically induce currents and get a magnetic field. So you have kind of like these helical structures that form because of the magnetic field. Yeah, right here, because the Earth spins and you have convection currents, all of these moving charges basically induce a magnetic field, and you can think of it kind of like a giant bar magnet deep inside the Earth. And so you've got a north pole and a south pole. Now, if you've ever looked at a compass, the red point north points north, which means that technically the northern geographic pole is the southern magnetic pole, and the southern geographic pole is the north magnetic pole. So it's kind of flipped that way, but for convention, we just call it the North Pole and the South Pole in the South. So the Earth has a magnetic field, and it's also a very complex system. The magnetic field is always changing and moving, and the Earth's magnetic field has actually flipped a couple of times over its history, and we have evidence of this buried deep inside rocks. So this is kind of what an example of the Earth's shifting magnetic field looks like. So it can actually flip positions completely. And up here, you see what the magnetic field, what the north magnetic pole looks like. It tends to wander about somewhere in the North Pole. So it's been in Canada and it's drifting over. So it's always constantly shifting. There's a lot of weird stuff going on deep below us. All right, so this is what the magnetic field looks like out in space. As I said, it's a pretty complex structure. So you've got the solar wind coming and interacting with the magnetic field, leading to what's called a magnetosheath. So this is where the solar wind kind of slams against the Earth's magnetic field. And over here you've got this region of lower density solar wind because it's protected, it's shielded by the Earth's magnetic field. And you can see there are these regions where electrons can travel through from the sun and make it all the way down here. We've also got these things called Van Allen belts that I'll talk about, but as you can see, there's a lot of stuff going on. There's a lot of lines, there's a lot of weird stuff. It doesn't really make all that much sense, but this is an image, this is an animation of what it would look like if the solar wind came and slammed into the Earth's magnetic field. So this region of like red stuff is higher density solar wind coming and slamming against the Earth. And you can see the field lines continuously changing. So some of them break, some of them reconnect at the back. So there's a lot of weird things happening, and the magnetic field is protecting us from solar wind. So what are those Van Allen belts? Well, basically there's the regions of space around the Earth because of our magnetic field, which form these donut-like structures, and there's two of them. And this is where, because of the Earth's magnetic field, particles, energetic particles, get trapped and they tend to stay there for a while. So the outer region, the outer Van Allen belt, this one in blue right here, contains a lot of electrons from the sun and the solar wind, whereas this red region called the inner Van Allen belt actually contains a lot of charged particles from the Earth's upper atmosphere. From way, way high up in the Earth's atmosphere, they get trapped here. And so these regions contain a lot of energetic particles, and this can actually be pretty dangerous for scientists or satellites around this area, because all of these tend to interfere with systems and can also be radiation that damages human beings when they pass through there. But luckily, astronauts who went to the moon were shielded well enough that they didn't face too much of a radiation risk when they traveled through these areas. So yeah, this is what this structure looks like. It's a pretty weird thing. You don't get to see it because these particles are really small, but it forms about 3 to 8 times the Earth's radius away from us. And so because you have particles that are orbiting the Earth and these particles have charges, basically you have giant amounts of current flowing around the Earth. And we call this the ring current. So there's actually a large amount of electricity flowing around the Earth because of the particles in Van Allen belts. And it's pretty energetic. And so when we have a solar storm that's pretty bad, or a CME, as Kumar explained, a lot more particles can get trapped in here. And so if you have larger amounts of particles, you get a larger current. And as Kumar explained, if you have a large current, you get a large magnetic field. And so this magnetic field actually counteracts the Earth's own magnetic field and can decrease the magnetic field that we see here on Earth, because we have a counteracting magnetic field that's generated high up in space. And so if you've ever taken a look at what the Earth's magnetic field strength looks like across the planet, you would expect it to be very strong at the poles and not as strong everywhere else. But it doesn't look so uniform as we'd expect. There's actually this large region right here over South America called the South Atlantic Anomaly, where the magnetic field is significantly lower than we'd expect. And that's because the Van Allen belts reach their closest point to the Earth. And so that magnetic field that they generate that counteracts the Earth's is strongest over here, and so we see a decrease in the magnetic field strength at this point. Okay, so there's a lot of weird things happening. The Earth's magnetic field is not as simple as just a dipole bar magnet. There's a lot more going on here. So yeah, I've talked about all these charged particles high up in the atmosphere. When you have moving charges, you get a lot of electricity. And electricity and magnetism are two sides of the same coin, as Kumar kind of explained. You have flowing currents, you get magnetism. So there's a lot of electricity high up in the atmosphere in the Earth's ionosphere. So when the sun is not really acting up and being crazy, the amount of current flowing through this region can be about 100,000 amps, which is quite a bit. And when the sun is unnaturally energetic, this can go up to 10 times as high, about 1,000,000 amps. So just to put into perspective, a regular lightning bolt strike has about 30,000 amps. So even on quiet times, this is about 3 times as much as a lightning bolt. And if you think about a 60-watt light bulb, that takes about half an amp of current. So this is a lot of electricity flowing here. And so these giant amounts of current flowing high up in the atmosphere accelerate particles, and small changes in the current can accelerate electrons, causing the aurora, basically. And so this region is actually called the auroral electrojet, which is this region where a large amount of electricity passes by, and so particles get accelerated, and they form the aurora. And this was actually first found out by Anders Celsius and Olaf Huerter. I might be butchering that second name, I'm sorry about that. But if Celsius sounds familiar, this is the very same Celsius that the temperature scale is named after, or centigrade if you prefer. But they found that if you had a compass high up at the poles when there were aurorae, you could see that the compass actually deflects, which means that whatever is happening with the auroras, something magnetic is happening here. It's causing compasses to deflect. Okay, so now let's come back. Kumar explained this, but I want to go over it again. What exactly are auroras? Well, they're electric phenomenon. And as I said, electricity and magnetism are just two sides of the same coin. So they are electric phenomenon that where you have energetic particles interacting with the Earth's magnetic field and particles of the atmosphere way very, very high up, when these energetic particles, mostly electrons from the sun, end up hitting these atoms or molecules of air up in the atmosphere, these atoms get excited, and then when they give off this energy, it comes off as in the form of light, which is why we see lights, because energetic particles hit the atmosphere gets excited, and then the atmosphere gives off light. Okay, so this is what we end up seeing. So what do you need to make an aurora? Well, you need energetic particles, mostly electrons. You need a magnetic field that they can travel along, and you need some kind of atmosphere that it can interact with that gives off light when it gets excited. And that's about it. All you need are these three things, and then you get an aurora, basically. So where do they form? They form, like I said, very, very high up in the atmosphere. So if you're wondering where space actually begins, we have set a standard called the Kármán line, and we say about 100 kilometers above sea level, about 60 miles, is the definition of the beginning of space. There's still atmosphere higher up there, but it's way, way, way less dense than on sea level. So about 100 kilometers up, it's the air pressure is a millionth that of down here on Earth. So the atmosphere keeps on going, but it exponentially decreases in density. So we just decided that 100 kilometers is where we'll say space starts. And so the auroras actually form around this region. They form at about the Kármán line, sometimes below, but it's mostly really, really high up. So at the edge of space, basically. And they also form around the magnetic poles in this area called the auroral oval. So they form around the poles because the Earth, like I said, doesn't have a uniform magnetic field. They form where the field lines meet the ground. And so you get like an oval called the auroral oval where you see aurorae form. So what do the colors mean? Well, the color depends on what particles of air that the auroras these energetic particles are interacting with. So our atmosphere is made up of an 80-20 ratio of nitrogen to oxygen, okay? And so when you have an energetic particle that interacts with an oxygen atom, it ends up giving off red light. If it interacts with a nitrogen atom, it gives off blue light. And if that nitrogen atom excites another oxygen atom, it ends up giving off green light. And then if you have a nitrogen molecule that's N2, not just N, it'll give off purplish crimson light. Okay, so these are the two main gases that interact with these particles and give off light. So red and green is oxygen, blue and purple is nitrogen. So those are the two gases that really interact with this. And if you're interested, this is a simple model of what an atom looks like, and depending on where the energy is released will give off a different amount of light. So not as energetic is red light, and then slightly more energetic is green light, blue light is more energetic, and purple is the most energetic. So this depends on the amount of energy that's transferred into these atoms or molecules of the air. And here's just a graph showing you how the amount of oxygen and nitrogen changes as you go higher up. So down here on sea level, there's that nice 80-20 mix. And then as you go higher, it decreases exponentially, basically. So that's what the colors mean. And if you take a look at it as a graph of altitude, this is what it looks like. So at higher altitudes, it's mostly the red color from atomic oxygen, not O2, just O. And then lower down, it's a little more green. And then towards the bottom, you get the effects of nitrogen, which means it's more blue or purple. Okay, so I've described that most of the auroras are made from electrons from the solar wind, but we also get this phenomenon called proton aurorae. And so what happens is sometimes protons that are stuck in the Van Allen belts can actually rain down on Earth lower than the poles. And so you get these regions where you have random spots of aurorae show up. So this is like an isolated proton aurora. Okay, and these are much rarer, but they're also more dangerous because protons are much more massive than electrons by quite a bit. So they carry a lot more energy traveling at the same speed. And so these proton aurorae can actually deplete or destroy the ozone in the atmosphere. So they can be a little more dangerous. And Sarah will actually mention some of this on other planets, but they don't happen that often on Earth. All right, so I'm going to show you an animation of what it looks like when electrons are accelerated and come to the poles and form the aurorae. So you can see solar wind hit the Earth's magnetic field, and then these field lines are about to connect again, kind of how Kumar explained. When field lines realign, it accelerates particles. So there we see the particles begin acceleration, and they follow the field lines all the way down to the poles. And this is how an aurora is formed. So solar wind interacts with the Earth's magnetic field. They get accelerated and follow magnetic field lines all the way down to where they interact with the atmosphere. They give off light, and we get an aurora. All right, so just because I can, and I like pretty pictures and pretty colors, these are some images that I took back in October in the UP. So this was a pretty major auroral event that happened. You can see the reds and greens of oxygen giving off light high up in the atmosphere. And here's other images where you can kind of see the greens, the reds, and a little bit of pinkish purple from nitrogen. But you get all kinds of colors. So you get purples from nitrogen, blues as well, and there's a lot of these. The aurora actually fluctuates a lot depending on how active the sun is. You can get auroras that pulsate or shift a lot around. And here's one from back in August on Bradford Beach. And so you can see the reddish purples up there, and more greens down below, kind of like how that altitude chart explained it. All right, so I've talked about the northern lights a lot. Most people on this planet live in the northern hemisphere, so we kind of refer to the auroras as the northern lights. But there are southern lights as well, and they form right above Antarctica in the auroral oval down there. And so the aurora borealis is a term coined by Galileo Galilei. Aurora comes from the goddess of dawn, and Boreas was the god of the cold northern wind. And the southern lights are actually called Aurora Australis because it comes from Auster, the god of the south wind. So you have the Aurora Borealis in the north and the Aurora Australis down in the south. And they're pretty much very similar because it's the same amount of atmosphere on both sides of the poles. But sometimes, in some cases, they can actually sync up and pulsate simultaneously if it's a strong enough event from the sun. So Kumar talked about forecasting the auroras. We can do this on different time scales. We can do it on long time scales by just thinking about when the next solar cycle is going to come. But our predictions on long time scales aren't as good as shorter time scales. We can also take a look at what the sun is doing a few days from when we expect to get a forecast, because we have satellites like the Solar Parker probe, which you may have heard of, actually touched the sun for the first time. It's the closest any man-made object has made it to the sun. So we've got things keeping an eye on the sun and tracking when these coronal mass ejections form, and so that can give us forecasts on the order of days or minutes. And we can also just take a look at sunspots, and we get an idea of, okay, the sun is being a little more active, and we might be expecting a few more aurorae to show up. So you can actually take a look at the National Space Service weather a website, and it'll give you a forecast of the auroras tonight and tomorrow. So if you see here, you can actually see that we are right below the view line for tonight. And so tonight is going to be a pretty energetic night. And so if you drive up north maybe an hour or an hour and a half, you might be able to see an aurora tonight if the weather permits. I know it's a little cloudy here, but tomorrow is not going to be as good a shot unless you plan on going to Canada. So it's a pretty useful website if you ever want to take a look. And this year is a pretty active year, so I recommend just always taking a look at what the forecast looks for the night off or the next night. So I've talked about aurorae, just a small amount on what humans think of aurorae. We've seen them for many, many years. Obviously, in the past when we didn't really understand what they were, it probably looked like magic. So if you've seen the movie Brother Bear, they kind of describe auroras as spirits of ancestors from Native Americans, and that is kind of one of the tales that people have told. So humans living around the poles, such as Scandinavia or the Maori or Aboriginals in Australia, have told stories about aurora for millennia. Some cases, the Inuit folk thought that the aurora was either a bunch of humans playing with a walrus skull, or in some cases, walruses playing with a human skull. I'm not exactly sure how it works, but there's been a bunch of stories. The Vikings thought it was the glow off of shields of their fallen brothers and sisters. So there's a lot of interesting stories surrounding them. And there's actually this one image from Spain dated back 30,000 years or 30,000 BC, where they think it might have been what ancient humans thought an aurora looked like. It's still a bit hard to tell, but the earliest recorded and datable event that was noted down was actually from China back in 1957 BC to 1977 BC, and they described auroras back then. So auroras have been around for a long time, but we've only just started figuring out what they are and how to predict them. And so I've talked about the Earth, and Sarah will go ahead and explain what auroras look like beyond just the Earth.
So, okay, so now I'm going to talk about auroras on other places on the solar system and even beyond our solar system. And before we jump into that, I just want to talk about recipes a little bit. So I hope that everyone have tried to bake or at least know how to do it, even if you haven't. And here I have a simple recipe that I would not recommend you to try, but of a cookie and a cupcake. And you see that the main ingredients are actually basically the same. You need flours, egg, milk, butter, baking powder, but then there's some things that changes. For example, for baking a cookie, we need more flour for less egg, and if you want to make like a cupcake or like a cake, we need more eggs for less flour. Also, in this example, I have like almonds in my cupcake, and in my chocolate chip cookie, I have chocolates. So for Aurora, it's the same thing. If you think about other planets, we will have the same main ingredients, which is having an atmosphere, having a magnetic field, and charged particles. But the amount of those things will change, and sometimes the composition. But in the end, they will make an aurora in the same ways that we can make cookies or cupcakes with just the same ingredients. And what I'm going to do is go through all the planets on the solar system and talk about the different auroras they have and why they are different from the ones we have here on Earth. And we will start with the beginning, with the closest planet to the sun, Mercury. And Mercury has an aurora in X-ray that was actually confirmed not long ago by this mission called BepiColombo, which is from the European Space Agency along with the Japanese Space Agency. And what they found is that, they confirmed, is that Mercury has a magnetic field that is very weak, but it does have one. So it's around 1% of the strength of the magnetic field of Earth. The issue with Mercury, and the reason why we wasn't sure if Mercury was able to make auroras, is because Mercury doesn't have an atmosphere. And we know that atmosphere is actually one ingredient to make an aurora. But it's the same thing as like doing cookies without an egg. It's possible. So actually Mercury does auroras, but what happens is that the charged electrons that comes from the solar winds reach the magnetic field lines, fall into the planet, and interacts with the surface of Mercury. And by interacting with surface of Mercury, it generates X-ray emission, which is what we see in Mercury's auroras. And just so maybe this is, like if this is not your first coffee shop presentation, or if you have seen other talks or videos about astronomy, you know about the electromagnetic spectrum. But if it's not, I always think it's nice to remember. We have here the electromagnetic spectrum, and the visible light is some wavelengths. X-rays is more energetic, which means that the wavelength is actually shorter. So we have visible, ultraviolet X-rays, gamma rays. Ultraviolet X-rays, gamma rays are more energetic than optical. And on the other side, we have infrared, microwave, and radio, which has a larger wavelength, and they are less energetic. So those auroras we cannot see with our eyes because they are not emitting in optical, but we can see with instruments that can detect X-rays. So next planet is Venus, and Venus has a different problem than Mercury, because Venus has a thick atmosphere, mostly composed of carbon dioxide. The problem with Venus is the lack of a magnetic field. So I'm actually kind of lying when I say that Venus doesn't have a magnetic field, because there's this, again, this mission here called Venus Express from the European Space Agency that discovered that Venus has a magnetic field that is induced by the solar winds. So when the solar winds reaches Venus and interacts with the atmosphere, it just generates an induced magnetic field. So what Venus doesn't have is actually a magnetic field that is formed inside the planet. So it's very different from Earth. And we actually have a little comparison here between Venus and Earth. And we see that Earth has this very rich and strong magnetic field, and Venus this very tenuous magnetic field tail. So the problem with Venus is the lack of magnetic field. And because of that, there were some discussions of whether or not Venus would be able to make an aurora, because it turns out that it's much harder to do an aurora without a magnetic field than without an atmosphere. And so we have this paper here in 2022 that they argued that they possibly have found an aurora, so it's possible that Venus have, and if it does, it emits in ultraviolet because of the carbon dioxide, and it's very, very faint. So what this paper did was actually measuring the solar activity near Venus with the Park Solar Probe, which is the mission that Joshua said that was reaching the sun. And actually, it make a little stop by, like a pit stop on Venus before reaching the sun. And while it was there, it measured the solar activity. And then the astronomers used models to see from that solar activity what strength of aurora they were expecting. And they looked from telescopes here on Earth to see Venus' atmosphere. And what they found was like this data here. And what they observed are like the black lines. And since the telescope was on Earth, we have this strong influence of Earth's atmosphere, which is like this blue curve here. But then we have this little extra bump, which they think is the very faint Venus auroras. So probably Venus does, but it's extremely faint, and it's on ultraviolet. So next planet is Earth. We've talked about Earth a lot, so I'm not going to talk about it anymore. I just wanted to do one last photo of it, so looking from space. So next planet online is Mars. And Mars have a magnetic field, Mars have an atmosphere, so Mars have everything it needs. But it's different from Earth, because the magnetic field of Mars is actually weaker than Earth, and it's not a global magnetic field. So I actually copied the quote that I saw on NASA website that was said from like an astronomer, because I couldn't set it better, so I copy exactly word from word, which is that Mars magnetic fields sprout out of the ground like mushrooms. So I have a little picture here. We see that they have like these little bubbles that just burst out of the surface. And those are Mars magnetic fields. And because it's not a global magnetic field and it's like spread throughout the whole planet, we don't see Mars auroras on the poles, but they are like across the whole planet because they will follow the magnetic lines, but they are kind of everywhere. And one nice thing is that actually looking to the auroras, we can kind of guess how the magnetic field geometry of Mars is, because we look where the auroras are, and there is probably the places that we see magnetic fields on Mars. So, and the same way as Venus, Mars auroras emits mostly in ultraviolet because its composition is carbon dioxide on the atmosphere, mostly. And auroras such as Earth has measured not only normal auroras that are made when electrons from the solar winds interacts with the atmosphere, but also the same proton auroras that Joshua talked about before. And there are two missions that were super important to study the auroras on Mars. The first one is MAVEN from NASA, and the second one is Emirates Mars mission, also called HOPE, from the Emirates Space Agency. So next planet is Jupiter, and Jupiter has the most interesting, richer, and nicer aurora on the whole solar system. So first thing is that Jupiter has, okay, we already have the video, so this is the sound of the radio emission of the auroras on Jupiter. And of course, the sound is, I'm going to let it play a little bit, and then I continue speaking. Yeah, so this is the radio emission of auroras on Jupiter. Of course, we don't hear the sound of auroras because they are electromagnetic spectrum, but what they did is get the same frequency of those auroras and make a sound of it. So this would be the sound of auroras on Jupiter. And they emit in several wavelengths radio, such as we've just heard. And then we also have infrared, optical, ultraviolet, X-rays. X-rays emission are periodic. They go up and down for each 27 minutes. And this specific recording we've just heard of the radio emission on Jupiter was done by this mission called Juno. So not only Jupiter has emissions in several wavelengths, but Jupiter has this aurora that never really shuts down. And there are a few reasons for that. First, Jupiter is actually able to trap charged particles in its atmosphere. But most importantly, Jupiter has a moon called Io, and Io has volcanism happening in it. And there are particles being released from Io volcans. And those particles go to the magnetic field lines of Jupiter, fall into the planet, and because of that, Jupiter has actually an aurora that it's always in some capacity present. So of course, the aurora changes when there's a solar wind. Of course, it evolves over time, but it's always there in some capacity. So it's a very interesting planet in terms of auroras. Next one is Saturn, and here we have images from Hubble of an ultraviolet emission of auroras on Saturn that happened in 2004. And we can see it starting and then starting the aurora, so it's fainter in the photo on the bottom. The bottom is the earliest date, and then it gets a little better, and then it starts to faint again. So Saturn's aurora emits mostly in ultraviolet. It does emit in other wavelengths, but ultraviolet is the way that it most shines because its atmosphere is mostly hydrogen. And it was detected by several missions, starting with the very early ones like Pioneer and Voyager. But I think the most interesting one was Cassini, which is a mission that went to study Saturn. And here we have a little video of Cassini showing Saturn auroras. I think it's a little hard to see, but Saturn is I'm gonna maybe play it again. Okay, so, oh wow, it doesn't. I'm sorry for that. I'm gonna play it again, but I'm gonna leave on this image. So, the black part is the planet. The lighter part are the background with the stars. And then we see this little line here, which are the auroras on Saturn. And moving forward, we have Uranus. Uranus, again, also have an aurora. It's fainter because it's really far from the sun. It emits mostly in ultraviolet, again, but we have detected it in infrared most recently. And one nice thing about Uranus aurora, which I think is the most different thing, is that it's not on the poles, because Uranus' magnetic field is actually misaligned with the axis of rotation. And it's the same thing that happens with Neptune. So I don't know if you follow NASA or James Webb Instagram, but they posted this photo this week. So if this presentation were to happen a week before, we wouldn't have this photo here because it was just released. But this is the auroras on Neptune that were first observed by James Webb Space Telescope and released this week. It shows Neptune's aurora in infrared. So we have the little auroras in light blue in this picture. So there's the comparison between Hubble and James Webb, and then we see the light blue part. And such as Uranus, Neptune has an aurora that is misaligned with the axis of rotation. So it's actually closer to the equator. So the auroras actually rotate along with the planet. And we don't necessarily need to restrict ourselves to planets. Moons can also have auroras. They only need to have magnetic field and atmosphere and be bombarded by particles coming from the sun or somewhere else. And we just see auroras on some places other than planets, such as some moons of Jupiter. So in this picture here, we have an example of Ganymede, and it's an ultraviolet aurora on this moon. And not only on moons, but we also can have auroras beyond our solar system. So of course, beyond our solar system, it's hard to measure the charged particles coming from to those stars or like planets, because we cannot measure the charged particles coming, but we can look at their light and see that the emission that we are seeing is very similar from what we would expect of an aurora. So I have here two examples of much likely auroras that we have already found that are not on our solar system. So the first one is from this object here. Oh, I'm sorry that I don't know what happened here. That was like 50 times Jupiter mass. So this object is something between a brown dwarf and a very light star. So it's actually not a planet. It's mostly a very heavy brown dwarf. And it has an emission that very much resembles an aurora. This is not the real picture of the brown dwarf. This is like an artistic impersonation. But this is the artistic impersonation that matches the observations we have. And another one is this other object. This one is something between a very massive planet and a very light brown dwarf. And we also have this emission that resembles an aurora. So it's very likely that we can also find auroras somewhere else in our galaxy, and we can detect them and compare to what we would expect from auroras of those objects. So it's very cool that we can do that. And so just to finish, we have the next talk on April 19th of the stars of our the star of our solar system. And before we actually wrap up and finishing everything, I just wanted to point out that Shashwat is actually graduating and moving to Texas next semester. So this is his last talk, and I think he should get a round of applause. Yeah, and with that, if you have any questions, you can ask us, and we'll be more than glad to answer.